Bournemouth, and the headquarters of the Lurvy Engineering Company Limited. And here we can see on paper what a modern aluminium plate mill looks like. The slab weighing over 12,000 pounds. The drive is to the work rolls, small diameter for maximum efficiency. The larger diameter backup rolls. As the name implies, they act as support for the work rolls and minimize their deflection during heavy reduction of the slab. The housings, immensely strong and rigid to ensure close tolerances in the thickness of the finished rolled product. Here in the drawing office, work is in progress on design and detail of the mill. The largest single items are the two roll housings, which will be made as steel castings, each weighing 180 tons. A steel casting rarely starts in the pattern shop. The wooden pattern is made in sections, here seen assembled into one piece for its finishing touches and final checking. We now move to the Grimesthorpe foundry of the English Steel Castings Corporation. On one day, it is possible to find as many as 8 moulds for mill housings in different stages. The initial preparation of the moulding pit floor is checked with the entire pattern in position. A bed is then prepared which will fit the contour of the underside of the pattern. This is faced with a highly refractory moulding material called compo. With the pattern finally assembled, sand is rammed firmly into the cavity between the pattern and the walls of the moulding pit. Compo is rammed against the actual face of the pattern to a thickness of about 3 inches. Refractory sleeves are embedded in the sand. These will form a passage through which the steel will run from one of the ladles during the pouring operation. Most of the top part of the mould is contained in 2 steel boxes. Compo has first been rammed against the top face of the pattern, then backed by old moulding sand. The contents are supported by bent rods, called lifters, which are hooked over the cross members of the box. When completed, the top parts are lifted clear of the pattern and the standing mould. The pattern is then removed, section by section, according to the prearranged plan. This must be done very carefully in order to avoid damage to the walls of the mould. The center portion of the mould contains a filling of ashes. This will provide a vent for escaping gases generated during the pouring operation and allows for contraction of the casting after solidification. Work commences on the preparation of all surfaces of the mould which will come into contact with the liquid steel. A sealing coat of refractory paste is worked into the coarse face of the compo. The undersides of the top parts are treated in a similar manner and later finished with a coat of refractory paint. The mould is covered with plates for drying. Portable gas-fired heaters force air into the cavity for a period of 10 days. Readings are taken both of mould moisture content and temperature, the latter being gradually raised to 500 degrees centigrade. In the meantime, the cores, which form the internal shape of parts of the casting, are being made. This cylindrical core is built up using a steel tube as initial support. The tube is first covered with asbestos rope. The main bulk is made up of refractory bricks cemented into position with compost slurry and reinforced by grids and wires. The outer surface is covered with compo. This is applied over a period of several hours, being gradually built up with finer gradings of slurry and intermediate bakings in the drying stove. An extra smooth mixture of compo is used during the final shaping. Other cores are made by ramming moulding material into specially made boxes. The material is supported by grids and steel bars. After a coat of refractory paint, the cores are dried in a stove. In here, the temperature will be gradually raised to 450 degrees centigrade for several days. With all parts of the mould thoroughly dried, the cores are carefully lowered into position. The cylindrical core will form the cavity for the screw-down mechanism, which adjusts the rolls in the mill. The top parts are then placed in position. Half of the mould is already covered by the top box seen on the right-hand side. The gap between this and the second top box is covered by two intermediate sections, one bridging each leg of the housing. With the final top part lowered, the delicate operation of closing the mould is almost completed. Feeder head boxes, lined with refractory material, are placed in position on top of the mould. These will contain reservoirs of liquid steel to feed the casting during solidification and contraction. In order to counteract the tremendous upward pressure which occurs during the pouring operation, heavy bars are placed across the top of the mould. They are firmly anchored to the sides of the steel-lined moulding pit. A plan diagram shows how the steel will be poured into the mould with two ladles at the opposite ends of the mould and a third in the adjacent bay. The liquid steel from the ladles will run into the mould through long refractory lined troughs. Over 200 tons of steel is required for the initial supply. It comes from 3 acid open hearth furnaces tapped simultaneously into the ladles. This synchronization requires coordination of the highest order, from the charging of the furnaces to the pouring of the steel into the mould. An exothermic compound is spread over the liquid steel in the feeder heads to prevent it from chilling whilst the casting is solidifying. Almost immediately afterwards, 3 electric arc furnaces are tapped to provide more steel for the feeder heads. Over a period of 7 hours, the supply to the heads is replenished from the arc and Siemens furnaces. After 2 weeks for cooling, the top boxes are removed and pneumatic chisels are used to chip the sand from around the feeder heads. The main bulk of the 2 feeder heads is then burned off. One man is using the oxyacetylene torch, the other holds a lance which provides the additional oxygen necessary to penetrate this thickness of steel. With the sand roughly cleared away from the top surface and part of the sides, the casting can now be lifted from the moulding pit. As the remaining sand is being removed in the fettling shop, we can now begin to see the shape of the immense casting. Work starts on the removal of the remaining portions of the 2 feeder heads. Firstly, a series of 1.5-inch diameter holes is drilled using a portable compressed air machine. This paves the way for oxyacetylene cutting and minimizes the stresses which would otherwise be set up by the use of the burning method only. The casting is now ready for annealing. This process refines the structure and reduces the stresses which were set up during cooling. The temperature in the gas-fired furnace will be gradually raised to 900 degrees centigrade and then slowly reduced, the entire cycle taking 17 days. The housing is now in the fettling shop and almost finished. The last of the surface irregularities are chipped away with pneumatic hammers, and the surface is smoothed by grinding. A crack detection test is carried out on all areas which will be machined. Iron powder is blown between the probes and will show as a thin black line if there's a crack. The immense load, weighing 180 tons, leaves the foundry on its journey to Liverpool, where it will be machined. Because of the problem of bridges, the casting is taken to the docks at Birkenhead and shipped across the Mersey by floating crane. Machining at Liverpool. In spite of the immensity of the workpiece, close tolerances for all machined surfaces are essential. As example, these faces must be accurate to within 5/1000th of an inch. We return to the Grimesthorpe foundry to see work starting on one of the 80-ton backup rolls for the same mill. Sand is first rammed into the cavity between the sides of the moulding box and specially made blocks of cast steel called chills. These are supported on the inside by a wooden plug. Finally, compo is rammed between the plug and the inside surface of the chills. With all sections of the mould completed and thoroughly dried, final preparations are made for their assembly in the casting pit, which is 25 feet deep. The mould is built up vertically in sections. A special parting powder is applied to check the accuracy of the joint between top and bottom parts. Old moulding sand is used as a safeguard against a possible escape of steel at the bottom. 100 tons of steel are required from 2 acid open hearth furnaces. Carbon electrodes are swung into position. A high amperage current will pass through them to keep the steel in the feeder head in a molten condition. This will then feed the body of the casting during contraction and solidification. After cooling for 3 weeks, the molding boxes are lifted off, one at a time. The casting is lifted clear, partly encased in sand. The upright columns are the paths which the liquid steel took when it was poured into the bottom of the mold through refractory runners. After machining, the overall length will be nearly 24 feet, and the barrel diameter 5 feet. After fettling, the casting goes to the machine shop. Turning is carried out in a large and powerful lathe. After rough machining, the roll is charged into an electric heat treatment furnace. Annealing, by heating and controlled cooling in the furnace, relieves the initial casting stresses. A second heating cycle further modifies the structure of the steel, after which the roll is withdrawn for cooling in air. When the barrel has cooled to the specified temperature, the casting is returned to the furnace for tempering. This treatment produces the required hardness and also improves the ductility and toughness of the material. The final operation is grinding to a high degree of precision. Returning to the roll housings, we find that machining has been completed. Careful inspection is essential to ensure that design tolerances have been maintained and that all parts will be in perfect alignment after assembly at the mill site. The first of the pair is now at its final destination, but the tricky operation of tilting such a bulk to the upright position has yet to be accomplished. When a certain angle has been reached, a specially made lifting tackle is fitted to the top of the housing for the final stage. The climax is reached, or nearly so. All that remains is exact positioning of the feet on the bed plates. both housings in position, the screw-down mechanism for adjusting the gap between the work rolls can now be assembled. The main worm and worm wheel for the first housing are lowered together, already in mesh. The main screw completes the link. Its lower end, projecting through the housing, will connect with the top roll chock. The roller bearings for the roll journals are contained in cast steel chocks. Finally, the rolls are inserted in the mill. The two work rolls in the center, the backup rolls above and below. A hydraulic ram pushes the entire bank through the window of the housing, the bottom chocks temporarily becoming wheeled bogies. And now the culmination of the skill of designers, mechanical and electrical engineers, forgemen, foundrymen, machinists. This latest wonder in the art of mechanization rolls into action. The aluminium ingots are heated to temperatures ranging from 450 to 550 degrees centigrade according to the alloy. They will be rolled into plates in thickness ranging from 5½ inches down to 1/4 inch, up to 11 feet wide and 38 feet long. Yet another service which James Booth Aluminium gives to the aircraft, chemical, shipbuilding, and many other industries throughout the world.